Okay, so let's start. I mean, it's possible that today's lecture might be a little on the shorter side, but anyway, it's a cool thing to know. So today the main agenda is going to be the Agrawal-Kayal-Saxena primality test. I guess this is going to be the most recent sort of algorithm we are going to see in this course. But again, recent also means that this is from 2002, so it's 20 years old. But nevertheless, it was a stunning result, and we'll see a full proof of it. And actually, the proof is surprisingly short. Of course, it's very clever. Okay, so I'm going to just recap a few things that we will need for today's lecture. Not really need, but it sort of helps set up the basic tools and so on. So we started off by doing the Miller-Rabin test. So even though Miller-Rabin is not going to be particularly needed for today's thing, it's good to keep in mind that all of these primality tests follow a particular template, which is that prime numbers satisfy a certain property, and this property will often be of the form, for all choices of a certain A, something happens. And you're somehow hoping to use this as a test to figure out if a number is not prime by just choosing an A at random and seeing if it fails this test. And in many situations, what will happen is that if you can show that there is a single point of failure, there are usually many points of failures. And so that often leads to some form of a randomized algorithm. So you can get a randomized algorithm out of this. Okay. And one particular thing algorithm that we saw, which was the Agrawal-Biswas randomized test for primality. And the main AKS primality test is very similar to that. One can think of it as a de-randomization of this test. So let's just go over exactly what the test was. So, I mean, barring some sort of silly cases that you solve separately. Like, for example, if the number happens to be a power of a prime, etc., those are things that you can discover. So the interesting situation is what you do is you want to check if this identity holds. That is x plus 1 power n equals x power n plus 1 modulo capital N. And we know this is a statement that is true whenever n is a prime. In fact, it's an if and only if statement. If n is a prime, if you expand this using the binomial coefficients, basically everything except the first term and the last term will be divisible by n, and therefore they will all vanish. But when n is not a prime, you can sort of show that some binomial coefficients do survive. So in some sense, you won't just get these two terms. So ideally speaking, this is the test that you may want to do. But the problem with this is that this is too large a test. Like, how am I going to expand out x plus 1 to the n? Look at all the terms and somehow convince myself that only these two terms survive. Because I want to run in time polylogarithmic in capital N. So the fix for this was, okay, let's just do one thing. We know how to compute this modulo some small degree polynomial. So let's just pick up a small degree polynomial of degree about log n or whatever makes the analysis work. Okay. And then basically just check if this equation holds modulo n and q of x. Okay. So that was the rough idea. Now, why did we think that, what is the rough intuition as to why this algorithm should work? So basically the point is, let's say, when will a choice q of x be a bad choice? A q of x will be a bad choice where this happens to be a non-zero polynomial, but unfortunately is divisible by q of x. Because then we are trying to somehow show that this is not equal to 0 for a suitable choice of n, some composite number n, but somehow it's equal to 0 mod q of x because of a stupid reason that q of x divides this polynomial. But intuitively speaking, the number of factors of this polynomial is perhaps far smaller than the number of monic polynomials you have of this degree. Or you set it up such that, intuitively you somehow say, if I pick a q at random, it's very unlikely that that q happens to be a factor of this thing. So this is a rough intuition. It needs to be formalized. It's not quite as simple because unfortunately this n happens to be a composite number. So the standard thing that a degree n polynomial has at most n irreducible factors, this is no longer true because you're not working over a domain sort of a thing. But the point is you can basically argue based on some prime that divides n and show that not only is this equation not equal to 0, it's also not equal to 0 modulo p as opposed to n. And then you're working over a field and everything sort of works. But it's not particularly important that you see the whole proof. But the point I'm trying to make is a rough argument as to why we would believe that this algorithm somehow gets it right with high probability. And this is roughly because of the fact that there are too few factors compared to the number of modic polynomials you choose. So, and somehow log n is good enough that you will get this with high probability. Okay, so now some facts we will need for today's today's thing is going to be these 3 facts that I will write down. All of them are very simple. They're all things that we have been using, in fact, a lot more generality in the previous lectures. But these are the 3 facts that I will just remind you of, which is that if F is a field and you look at this sort of extension where you artificially add an element that satisfies the polynomial h of x, if h happens to be irreducible, then this object also happens to be a field. And this was how we were constructing finite fields of size p power k, etc., because we would start off with f being fp, and then basically adjoin, or rather go quotient modulo some irreducible polynomial of degree k. Okay, so that's one fact. And it's also good to sort of mentally think of this as saying you are artificially adding a root of h of x to the field f. And you're looking at the smallest thing that contains that one root of f. And it just turns out that if h was irreducible, then what you end up with becomes a field. Okay. And this is the second one is the degree mantra, which is that over a field f, a non-zero degree d polynomial can have at most d roots. And this is often going to be used to sort of say that you want to somehow show a certain polynomial as 0. And you often do that by exhibiting that this polynomial has more roots than its degree. So it better be 0. Okay, but again, it's important that it's over a field. So often we'll have to appropriately change our domain to make this work. And finally, this is something that we often ask in our interviews and stuff like that, which is that you're given a number n and you want to check if this number is of the form a power b for non-trivial a and b. And there is an efficient algorithm to do this. And I presume that this is something that you know. Okay, good. So these are the basic facts that we will need. And I'm going to write down the entire Agrawal-Kayal-Saxena primality test. I will say out of the outset that I think the numbers that are used here are slightly different from what I described in the previous, the sketch in the previous lecture. And this is mostly because I have made absolutely no attempt to try and optimize these numbers. It's just something to show that this is a polynomial time algorithm. Of course, there has been subsequent improvements in reducing these numbers, but we are not really going to bother about this. The goal in today's lecture is to just convince us that there's a polynomial time algorithm. Okay, so here's what we are going to do. Step 1 is you do one of your easy tests. If a number happens to be a power of something, then you know it's composite, so you say it's composite. Otherwise, you set these bounds for R and A. And the first thing that you check is if there are any small prime factors for it. Okay, that is, you try out all R from 2 to capital R or something, and if any of those things divide my number n, you just return composite. Again, these are easy tests. Otherwise, you do this Agrawal-Biswas sort of test, where instead of x plus 1 to the n, you are now looking at x plus a to the n. Nothing really changes. But you go modulo x power r minus 1. And you're going to run this test for various choices of r and various choices of a. Okay? And if any of these tests fail, that is, by fail I mean if any of them is non-zero, modulo n and x power r minus 1, then in some sense you found a certificate that your number is composite, so you can return composite. And the key part is if by this time you have not found that the number is composite, then the number has to be prime. Okay, so this is the overall algorithm. And we want to argue that this algorithm does indeed give the right answer. One thing that is absolutely clear is that this is a polynomial time algorithm. It runs in polynomial time in log n. I presume the way I have described it, these two for loops is already something like log n power 12 or something, plus some sort of chiller work for figuring out this thing. So, but again, we are not going to worry about the running time at all. I mean, it's just to show that this is a polynomial time algorithm. Okay. So let's first look at what are cases where we know that the algorithm gives the right answer. So there is a bunch of easy cases. So the algorithm always gives the right answer in the following setting. If n happens to have a small prime factor, by small I just mean a prime factor smaller than log n per 7. Okay, then we know that the algorithm is going to correctly return composite because of this step. Okay, and if n is a power of another number, then the first step itself would have figured that out. So therefore, there also I know that the algorithm is going to work. And furthermore, if n is actually a prime number, notice that all of these tests will actually, I mean, each of them will be equal to 0. Okay, so therefore we know for a fact that we will not return composite, and therefore we will end up in this situation and we'll return prime. Okay, so the interesting setting is when we want to say that if a number has at least 2 prime factors, and if both those prime factors were largish, by that I mean it's bigger than this log n per 7 or something, we want to somehow argue that the algorithm does correctly output composite. Okay, that is, or in other words, one of these tests must fail. I mean, so one of these things must be non-zero mod n and x bar r minus 1, and that's what we want to argue. Okay, so what we are going to basically, the rest of the algorithm is going to say, let's pick up an n that supposedly has at least 2 prime factors, both of which are this large, but somehow the algorithm is magically returning prime. And we'll want to say that, no, this can't happen. There is some contradiction here. Okay. So what are we given? We are told that n is apparently a composite number. It has at least 2 prime factors. It's not a power of something. And both the prime factors are large, but somehow magically all these equations hold. Because that's the only way I will return prime. I will return incorrectly prime. And we're going to assume that this happens and figure out why should there be a contradiction? Like what goes wrong? Okay, so that's what we are going to figure. Okay, so let's intuitively try and get a sense of, I mean, the potential difficulty in somehow, I mean, I don't know how to say this differently, in the sense that why is this a very non-trivial statement to make? Okay, so the reason, in my opinion, is the following. So suppose n was a composite number. We know for a fact that this polynomial, x plus a power n minus x power n minus a, this is not equal to 0 mod just n. That is, if I hadn't gone mod x power r minus 1, then I know for a fact that this is a non-zero polynomial. Okay, but I mean, it may be that, you know, maybe x minus 1, x squared minus 1, blah, 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 all the way till x power capital R minus 1, it divides this nonsensical polynomial. Okay, I mean, because notice the left hand side is something that has degree which is roughly polylogarithmic in capital N, whereas the right hand side is some polynomial of degree capital, or maybe capital N minus 1 or whatever. It's a massive degree polynomial. So, but it feels like the number of tests I'm doing is far smaller. So for all you know, it could be the case that all of these guys just divide this. Okay, and maybe the same thing is true for all of them. Maybe it's also true for x plus a power n minus x power n minus a. I mean, on the face of it, it feels like this entire set of equations is basically saying that some bunch of polylog n degree polynomials divide these sorts of polynomials. And on the face of it, it feels like, yeah, why not? I mean, like, you know, maybe that can happen. So the question we want to get a sense of is, how do we really rule this out? By which I basically mean that it seems like we have polylog n, I mean, in a vague sense, information, but an n degree poly. We are somehow trying to argue that a degree n polynomial is 0 by something that looks like polylog amount of information. Okay, it's a little vague at this point, but I'm just saying that on the face of it, it feels like, well, this could be true. Maybe it's true for all of these things. How do we somehow argue this? And I'll roughly, I mean, things will become clear as we go along. What I want is some form of what I'll try to call a witness explosion. I mean, I'll eventually want to argue that this polynomial is 0 because too many things divide it, or some version of that. But at the moment, it doesn't feel like I have too many things that divide one polynomial. So what we'll try to do is we'll try to use these equations to somehow come up with some other impossible situation to somehow get our contradiction eventually. Okay. So that's what we're going to do. We're going to just proceed with this slowly and see how to do this. So we'll need a bunch of notation. Okay, so the first notation I'm going to define, I mean, I don't know if I explicitly mentioned this while doing group theory or something. So there is this general notion of what is called an order of an element. And normally you put an R here to mean that you're interested in the order modulo R. Okay, and it just refers to how many times do I need to keep powering it until it becomes 1. And naturally, this makes sense only when M is co-prime to R, because otherwise, if M and R have a common factor, I'm never going to get this at all. But nevertheless, you just say what is the smallest I such that M power I is congruent to 1 quarter. Okay, so let's start with the first lemma, which is that in the range of R's that we were looking for, one of those R's must satisfy this property. In fact, once we find such an R, the rest of the proofs, we can just fix that R and work along. You don't really need to try out many R's. The reason for trying out many R's is so that you're looking for an R that has this property. Okay, so this is the first step we are going to argue. And okay, and it's one of these, you just write down what you need, and then it's a very simple lemma. Okay, now let's ask ourselves, what is a bad choice for, or rather, not instead of what I want is when is a, I mean, what sort of choices for R are bad? I mean, I'm a horrible grammar, but nevertheless, at least you understand what I mean. So when will an R be bad? If it so happens that for that value of R, n has much smaller order. Okay, so that means that one of the following must happen. So either R divides maybe n minus 1, or R divides n squared minus 1, or R divides n power whatever 5 log squared n minus 1. Or I mean, I want order to be strictly bigger than 5 log squared n. So therefore, these are all choices of R where the order of n will actually be smaller than our target. Okay, so if this happens, then an obvious thing is that R must divide this big product n minus 1 into n squared minus 1 blah 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 till n power 5 log squared n minus 1. Okay, what's a stupid bound on the right hand side? So this is at most n, this is at most n squared, n cube, all the way till n power 5 log squared. Okay, so this is at most n power summation I going all the way till 5 log squared. Okay, which if you, I mean, this is just going to be something like what, 20, sum till k roughly looks like k squared by 2. Okay, so you're going to end up with something, I don't know, which is something like 12.5 log power 4. So an n is, I mean, an R is going to be bad if you just got unlucky and your R happens to divide this, or rather, all bad R's divide this big number. Okay, and now let's ask ourselves, how many different prime factors can this have? Okay, so this number has at most something like 12.5 log power 4, log power 5n or something. Basically, a number can have at most logarithmically many prime factors because each prime is at least 2. Okay, number of distinct prime factors is at most this many prime factors. Okay, but the set of numbers all the way till, I don't know, log power 7 or something is going to have at least log power 6 many primes within them or something. Okay, so this has at least log power 6 and many primes among them. Okay, I mean, this is a very bad bound in the sense that up till r, you will have roughly r over log r many primes that you see in the first r numbers. And I'm just crudely saying that it's at least log power 6. And I'm saying there are 12.5 log power 5n bad primes. So therefore, one of these should work. Some r in this range will be. Okay, is this okay? It's a very simple thing to just say that the number of bad choices of R is actually quite few. So if you just go to a sufficiently large range, you will find one R that does not divide this number, and that's good enough. So that will tell us that n has a suitably large order modulo R.
Okay, that was just you just use the density of primes. Right?
Yeah, I'm just using the density of primes to mean that this has roughly R over log R many primes. Yeah. Okay, good. So what does this tell us? So this tells us that therefore, so let's fix a good R, or fix an R in R such that the order with respect to R of n is at least, I don't know, something like 5 log squared n. Okay, so notice that this also implies that one of the prime factors that divide n, okay, or rather some p that divides n must have order R of p. I mean, this must be, it better be at least 2 or more. Because if all the prime factors are of the form 1 mod R, then n will also be 1 mod R. And how can the order of n be as large as 5 log squared n or something? So it better be the case that one of those prime factors has a non-trivial order. And by non-trivial, all I'm saying is that it has order at least 1. Okay, so the rest of this, the rest of the argument, we are basically going to fix this R and P. Okay, so the for loop that went over all R was just to make sure that one of the R's is good. But if you know beforehand that this R is good, you can just fix that R and do just the for loop over A. Nothing would have changed at this point. Okay, so far so good. I hope people are with me here at this point. Okay, so now what I want to do is I want to get the witness expression. I mean, and it's one of these things where once I write down what I mean by this, things should hopefully become a little clear. Now, at this point, what we know is that this statement is true for all choices of A in that certain range that you have. Okay, and it's going to become a little annoying that n is not prime and x bar r minus 1 is not irreducible. Because I would like to think of this as a statement over a field. And unfortunately, the right-hand side, I'm going modulo things which clearly are not going to give me a field because n is not a prime and x bar r minus 1 is not irreducible. So going mod n is not helpful in some. I mean, at the moment, it feels like it's an annoying situation. So what we are instead going to do is we are going to weaken this statement. I know this is true for all choices of A. That is, this is true for all choices of A, which means in particular, it is also true when I replace n with this prime factor p that n has. And furthermore, I replace x bar r minus 1 by whatever is some largest degree irreducible factor for x bar r minus 1. Okay. So just pick h of x to be the largest degree irreducible factor for this thing over fp. And whatever that is, we are going to write down the equation just modulo h of x. Okay. And if you think about it, what should h of x actually be? The smallest degree irreducible factor will sort of amount to what is the minimal polynomial that a primitive rth root of unity satisfies. It's like you are adding a primitive rth root of unity to fp. I mean, it's like, if you're looking at x cubed minus 1, you want to remove x minus 1, and now you have 1 plus x squared, which omega and omega squared satisfy. So it's like as if you're adding that particular omega to the thing. This is intuitively what is happening. But algebraically, if you want to ignore this, you can basically say that, let's just pick up the largest degree irreducible polynomial of this guy and just go and just treat the equation here. Okay. And why am I doing this? The reason I'm doing this is because if I think of this object, which is fpx quotiented by h of x, this is a field. Okay, that's the reason we are doing this, because we would like equations over fields, because at some point we're going to use the degree method. We're going to basically say there are too many roots and etc. etc. Okay, and what field is this? This is basically adding a primitive rth root of unity to fp. That's intuitively what this field is. Okay, so far so good. Okay, good. So what do we know right now? We know that if I think of x as an element in this field, then I have an equation of the form x plus n the whole power, x plus a the whole power n equals x power n plus a in this field for every choice of this value a. Okay. Furthermore, I have this just from the binomial. Because instead of n, had I replaced it with the prime p, then also the same thing holds. Because I know x plus a the whole power p equals x power p plus a mod p. But mod p is already taken into account here because, you're working over fp. Okay, so we are going to take these two equations and use that to come up with a weird definition, which is, I'm just going to borrow the same notation that is used in the Agrawal-Kayal-Saxena paper, which is to say that we will say an integer m is introspective for a number, for a polynomial f, if it so happens that f of x bar m equals f of x bar n, that is, this m sort of enters the bracket, inside the bracket somehow, modulo p and x bar r minus 1. So in particular, if this were true, then f of x bar m will be equal, f of x the whole power m will be equal to f of x bar m over the field f also. Because it's certainly true modulo p and n, so therefore it will be true modulo p and h of x as well. Okay, this is just a definition of what is.
We saw something similar in an earlier lecture, right? When one of the cases that we were handling, maybe was in this was in, I guess, factorization, where we said,
so that was when the derivative was vanishing or something like that.
Then it would have to be a point where you can x to the k divides every term.
Yeah. So this one is somehow special, which is coming from the fact that this is what I know. So in some sense, I would like to say that capital N is introspective for polynomials of the form x plus a, and p is also introspective for polynomials of the form x plus a.
Oh, okay.
So this is what I have. This is the data that I have, and I want to somehow say, oh, this means a bunch of other things happen, and at some point an impossible thing will happen. Okay. So this is the definition of what introspective means. It just means that somehow m goes inside the bracket when you look at this modulo p and x bar r minus 1. Okay. So here are a couple of very simple observations, which is that, this introspection sort of somehow satisfies some form of product, which is that if I have a number m, which is introspective for both f and g are two different polynomials for which this is true, then it's certainly introspective for the product. And this is a completely trivial statement to make, because what do I want to show? I want to show that f of x, g of x, the whole power m, which is the same thing as this. I mean, this I know for a fact that f of x is equal to f of x power m, and g of x is equal to g of x power m, mod p and x power r minus 1. Right? I mean, it's just trivially true. There's really nothing to be done here. So certainly fg satisfies this property. The more interesting situation is the product rule of the other type, which is that when I have two different numbers, m1 and m2, that is introspective for a single polynomial f, then its product is also introspective for that polynomial. Okay, this requires a bit more work. Okay, so let's start with what we have. So let's look at f of x the whole power m1. This we know is equal to f of x power m1 mod p and x power r minus 1. Now, what I'm going to do now, what does this mean? It means that if I take the difference of these two, all terms are divisible by either p or x power r minus 1. So in this equation, let me just replace x with x power m2. Okay, so this implies that f of x power m2 the whole power m1, this is equal to f of x power m1 m2, but notice that this is going to be mod p and x power m2 r minus 1. I've just replaced x with x power m2. Okay, but notice that x power r minus 1 always divides x power m2 r minus 1. So the above equation basically immediately means that f of x the whole power, I mean, this I know is equal to f of x power m2 mod x power r minus 1. So you basically get this power m1 m2 equals f of x power m1 m2 mod p and x power r minus 1. Okay, that's it. So it's just one extra trick is that we can replace x with x power m2 throughout, and this automatically implies that it's not only 0 mod this, it's also 0 mod x power r minus 1. So we can repeat the process. Okay, so what does this tell us? It tells us that if m is introspective for f, then in particular in this field, I know that this happens. Because this field is going modulo h of x, but the introspection is actually modulo of multiple of h of x, which is x power r minus 1. Okay, so what do we know so far? I know p is introspective for x plus 1, x plus 2, blah, 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 till x plus a. Okay, that's what, I mean, this you get just from the binomial theorem. From the fact that the test has succeeded so far, I know n is introspective for x plus 1, x plus 2, all the way till x plus a. So for every element on this side happens to be introspective for every element here. Okay, what does this mean? This means that p power I times n power j is introspective for, I mean, I don't know, something that looks like, I don't know, you run over all possible t and then you take x plus I power ei or something. Basically, any product involving p and n on the left hand side is going to be introspective of any product involving these a elements, because that's what the previous two observations tell us. If I have two numbers that are introspective for a polynomial, their products are, and similarly, if it's introspective for two different polynomials, it's introspective for their products also. So suddenly, I have a whole bunch of numbers that are all introspective for a whole bunch of polynomials. Okay, and in some sense, I want to say this is the witness explosion.
Hey, sorry, just got one thing. What was the capital T here?
So this, I'm just saying that, it could be some product of the form, let's say I going from 1 through capital A, where EIs are your chosen favorite
I mean,
integers.
just saying some product.
Yeah, any sort of product involving these numbers. I mean, these polynomials. Somehow you have that for every such integer of the form p power I n power j happens to be introspective for all of these sets of polynomials. So suddenly it feels like a polylogarithmically many equations that you had has now led to a whole bunch of other equations. And to me, it's at this point that you start having some belief that, okay, some contradiction is close by, because this feels too good to be true. I mean, there are too many such equations that are happening, and somehow we want to say that, no, there's something that's going wrong. Okay, so that's the thing. And now the rest of the lecture is just going to be to formalize exactly what is going on, what has happened here. So let's set up some notation. These are the sort of numbers that happen to be introspective. And since we are going modulo x power r minus 1, it's like as if every time you see an x power r, you're going to replace it with 1, right? So the interesting situation is you want to understand what are all the numbers that look like p power I n power j when you think of them mod r. Okay, let's give this a name. Let's call that this group G. So G is just going to be the set of all the subgroup of ZR star that is generated by P and N. I mean, I don't particularly know how large this group is or something, but I'm just going to look at all possible elements I could obtain in this process. Okay, so far? Okay, good. And let's say the size of this group is, I don't know, some T. I don't know what the size is. Let's just give it a name and let's say that there are T elements in it. I want to know what are some stupid upper bounds and lower bounds. Okay, one trivial upper bound is that this is at most this small r, because they are subgroups of ZR star. And this I know is at most this capital R, which was, I don't know what we had, some log n per 7 or something. So this group is not too large, but I want to say it's not too small either. So can you give me a lower bound for what this group is? How many elements are you assured that this group must have? This is where the choice of R is important. So we chose R a certain way. So far, the only thing we've used about R was that the order of n modulo R was at least, I don't know, something like 5 log squared n or something. Okay. If I forget all these elements and just look at n, n squared, n cube, n power 4, etc., how many different elements will I get? That's exactly equal to the order of n modulo R. So therefore, this is at least as large as the order of n modulo R. Okay, and this we set it up such that this was something like 5 log squared. Or sorry, not equal. That is, it's at least as large as 5 log squared. So we know that currently this group is large enough. I mean, like in the sense that it's not tiny, it's at least 5 log squared n. And furthermore, we know that it's not too large either, because it eventually happens to be a subgroup inside ZR. And R was not large to begin with anyway. Okay, so much for what this is. And by the way, I also want to mention that notice that P is at least as large as capital R as well. P is bigger than capital R, because I mean, if it had a small prime factor, we know that we would have found it anyway. So we are interested in a situation where n only has large prime factors. Okay, so this is so much for the left-hand side in this introspection equation. All the p power I n power j is what we are trying to understand. Now let's look at the other thing. These are all elements of my field capital F. Okay, x plus 1, x plus 2, they're all elements of my field capital F. I want to know if I just look at all possible products among them, that is all of expressions of this sort. Okay, I'm going to get something. I'm going to get some subset of this field. Okay, and I'm going to call this my set capital S. Because basically the previous equation is saying that every element of G is introspective to every element in S. So we're trying to get a sense of what the size of these things are to get our desired contradiction and say that something really bizarre is happening. Okay, so what we are going to do is we're going to prove two bounds for the size of this set S. On one hand, we will show that this S is not too large, which is roughly something like 2 square root t log n or something. But on the other hand, we will say that S has to be at least as large, like S is rich enough to mean that there is a substantial number of elements in S. Okay, and before we prove these two claims, notice that this automatically means that something really absurd is happening. But this is absurd as the lower bound, which is min of 2 power t minus 1 and 2 power a, this is actually bigger than the upper bound. Okay, for our choices of let's write this a little. Okay, and why is that? Because I don't know which of the two is the smaller quantity. Let's just show that both of them are bigger than the right hand side. Okay, now, so notice that when will this be bigger than this quantity? So roughly you want this t is bigger than 2 square root t log n. Okay, which is the same thing as saying that square root t is bigger than 2 log n. But I know that t is like 5 log squared. So square root t is certainly bigger than 2 log n. Okay, so this basically tells us that 2 power t minus 1 is much larger than this guy anyway. Okay, and what can I say about 2 power a? Now a we had, chose it to be something like log power 5n or something like that. Okay, so 2 power a is something like 2 power log power 5n. But what's the largest that this quantity can be? Worst case, t is maybe as large as, log n power 7. So square root t is going to be something like log n power 3.5. There is one extra factor of log n. So it's like log n power 4.5. So this is certainly bigger than 2 power something like 2 into log n power 4.5. Okay. So that basically is going to tell us that, well, if these two claims are true, then clearly we have a contradiction. Okay, because the lower bound appears to be larger than the upper bound. So clearly something wrong is happening. Okay, so therefore the rest of the proof is just to somehow show that these two claims are going to hold. And both of these are just a use of the degree mantra once you set up the equation correctly. Okay, so let's just prove these two upper bounds. The upper bound and lower bound. The first thing I'm going to show is this. I'm going to show that the size of S is not too large. Okay, so far so good. I hope people are okay. Good. So now what I'm going to do is the following. So this is the set G that I have, and I'm told that size of G is equal to T. Okay, and I want to somehow use this to bound the size of S by about 2 to the square root T log n, or n to the 2 square root T or something. Okay, so here's what I'm going to do. I'm going to consider the following set of elements: n power I, p power j, where both I and j is at most square root. Okay, this has how many? Okay, I want to say how large is this set? Well, I have square root t plus 1 choices for I, square root t plus 1 choices for j. So therefore, overall has at least square root t plus 1 the whole squared, which is strictly bigger than t. distinct integers. Okay, and let me just add, why is this distinct? Why are all of them distinct? I want to somehow say for different choices of I and j, I will have two different integers. They won't be the same. Okay, here it is important that n has at least two prime factors. That way, if let's say q was the other prime factor, the power of q that divides this is going to tell you exactly what I is. And the offset in terms of how the power of p that divides it will tell you what j is. Okay, I mean, this would not have been true if n happens to be a power of prime itself, because there could be different ways of getting n power I, p power j to be the same. But if you know for a fact that n has at least two prime factors, all of these are distinct integers. Okay, is this okay so far?
Can you go over this again? Why,
okay, so let's say that let's say n is divisible by, I don't know, q power a. Q is some other prime number. Okay, then n power I, p power j will be divisible by q power a times I. So if somebody just gave you this number m and asked you, can you figure out what I and j are? By looking at the power of q that divides this number, you will know what I is. You account for whatever the contribution of p from n is going to be, and all extra contribution must have come from this j.
Yeah.
So if you know n has two different prime factors, n power I, p power j will all have to be, I mean, given n power I, p power j, you will know precisely what I and j are. Okay, so this is a bunch of greater than t many distinct integers, but apparently they're all, if I consider them modulo r, I mean, it's in some set of size equal to t. So this implies there exists some n power I1 p power j1, which is equal to n power I2 p power j2 mod r. Right, because all of them are elements inside this. If I consider them modulo r, they're all elements inside this group G. But I have t, at least I have more than t elements, and the group G only has t elements. So some two of them must have given the same element. Okay, and let's just call this number as m1, and let's call this number as m2. Okay, and notice that both of these numbers is at most n power 2 square root. Because, I mean, both I and j are at most square root t. So worst, I'm just saying that this is at most n power square root t, this is at most n power square root t. So overall, in terms of actual numbers, they are at most n power 2 square. So far, so good? Okay. Now, what we are going to do is the following. Now, let's look at the following polynomial, p of z, which is equal to z power m1 minus z power m2. Okay, so this is obviously not equal to 0 because m1 and m2 are two distinct integers. Okay, so it's not equal to 0 of degree at most n power 2 square root t. But how many roots does this have? Okay, so if you pick up any f inside this set S that the set of introspective numbers that you had, okay, then f of x power m1 minus f of x power m2, what is this going to be? This is going to be equal to f of x power m1 minus f of x power m2. I mean, all of these are equations inside this field f. Okay, but this is nothing but f of x power m1 mod r minus f of x power m2 mod r. But we set it up such that m1 mod r is equal to m2 mod r. So therefore, this is equal to 0. Okay, so this basically tells us that therefore every f in this set S that you had, which is a subset of my field F, okay, is a root of P of Z. Okay, and I know for a fact that P of Z is not equal to 0. So it could not have had more roots than its degree. So this implies that the size of this set S is at most n power 2 square. Is that okay? So let's just go over this once more. So we started off by saying that, well, if you tell me that the group has size at most t, here are more than t many elements that all happen to be in the group if I consider them modulo r, but they're all distinct integers to begin with. So pigeonhole principle will tell you that two of these numbers must be the same when you consider them modulo r. So let's just fix those two integers, m1 and m2. And we then said, let's look at this polynomial, which is just z bar m1 minus z bar m2. Because m1 and m2 are different integers, this is a non-zero polynomial. And by the sort of bounds that we put on I and j, the degree of the polynomial is not too large. But on the other hand, I want to say every element of the set S that we wrote down above actually satisfies the fact that this equals 0. Now, why is that? Let's just take this f and plug it into this equation. I will get f of x bar m1 minus f of x bar m2. But I know that m1 is introspective for f because f was an element of the set S. So therefore, this is equal to f of x bar m1 and this is equal to f of x bar m. And in the field f, I know that x power r equals 1. So therefore, x bar m1 is the same thing as x power m1 mod r, whatever was the residue modulo r. So this basically says that I have f of x1, x bar m1 mod r minus f of x bar m2 mod r. But we set it up such that m1 mod r equals m2 mod r. So we're literally subtracting the same thing. So therefore, we are going to end up getting 0. So this tells us that here is a polynomial of degree at most n power square root t, and every element of S is a root of this polynomial. So this automatically forces us to admit that, okay, then in that case, the size of the set S could not have been larger than the degree. So it has to be at most n power 2 square. Okay, so this is the upper bound. To sort of say that size of S can't be too large. Okay, so is this okay, or should I maybe go over this part again? Okay, so it seems to be fine. So now let's prove to the lower bound. Okay, now, okay, so let's get a sense of exactly some very basic facts that we'll need. So this is the field that we are working with. Okay, fpx quotiented with hx, and hx was this, whatever the largest degree irreducible polynomial for x bar r minus 1. Okay, this is some field f, but we know that this is actually fp power k, where k is the degree of this polynomial h. Okay, now, okay, so now notice that, how do I put this correctly? So, I mean, I know that x power r is equal to 1 in this field. Okay, so this in particular implies that r must divide p power k minus 1. Because every non-zero element here satisfies x power p power k minus 1 equals 1. Okay, and this was one of the simpler constraints that we had here. So now, so therefore, so this implies that p power k equals 1 mod r. Okay, and this implies that whatever this k is, it better be at least as large as the order of p mod r. Right, because order of p mod r is the smallest value of k such that p power k is 1 mod r. Okay, so this is what happened. So this, and we set it up such that this was at least 1. Okay, so the only thing I'm trying to tell you at this point is that the polynomial h is at least a quadratic. It's not a linear polynomial. That's all I'm trying to say at this point. Okay. Now notice that we also set it up such that there are no prime factors of n which were smaller than this number r, because we had eliminated that in one of the tests that we had done. So we know that any prime factor that n has must satisfy that it is bigger than r, and r was anyway bigger than a. So therefore, this is one thing that you have. What does this tell us? It tells us that x plus 1, x plus 2, blah, 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 till x plus a, they're all distinct elements in this field F. We are trying to somehow show that the size of the set S is large. Right now, I know that there are at least A elements in it. Okay, but I want to say more. I want to say that no, it's not just them. There are many products that you can take among them. They will also be distinct. Okay, that's what we are trying to somehow show. So we will show that any T product of these, or rather, how do I put it? I'll say that any less than T product of these will also be distinct in F. That is, as long as you're taking a product of fewer than T of them, I want to claim they will all be distinct elements as well. Okay, now why is that? Let's just do the following. So let's just say that f of y is one such product. Y plus I belongs to some set T1, and this whatever, this T1 is some subset of these factors, and the size of T1 is less than T. Okay, and similarly, G of y is another such product. Okay, T2 is a subset of A, and oh, maybe there are repetitions, etc. There are probably powers that are going on. I'm just ignoring all of them. T2 is also strictly smaller. Okay. Now, right now, as polynomials, they are different. But we're not interested in them as polynomials. We want to know if I plug in y equal to x, what happens? Like as elements of the field, what happens? Okay. So, I mean, we'll do the one thing that we know, which is let's just define q of x to be f of y minus g of y. Okay, I know this is not equal to 0, and this has degree strictly smaller than t. Okay, and I want to somehow argue that this has way too many roots in it. Okay, now notice what one thing I know is the following: q of x is equal to f of x minus g of x. Okay, so this is what I have, and I'm somehow trying to argue that many of, I mean, let me not write this way. So what I'm going to do is I'm going to look at q of x power m, okay, where m is taken from this group G. For any choice of m that's coming from this group G, what is this equal to? This is f of x power m minus g of x power m. Okay, but I know for a fact that how do I? Okay, so what exactly am I doing here? Sorry. Let me just step back a little. So we are basically trying to show that these sets of polynomials are all distinct. So on the contrary, suppose someone told us that, look, here is one polynomial and here is a different polynomial. But somehow this is a non-zero polynomial of degree t, but q of x, which is equal to f of x minus g of x, this is equal to 0 in the field F. Because this is what I'm trying to we are somehow trying to argue that these two, as elements of F, they are distinct. But suppose not. Suppose someone told us that no, I have actually two different polynomials such that the difference actually happens to be 0 over the field f. Okay, we are trying to somehow argue that no, that can't happen. Because if this happens, then q of x power m, which is equal to f of x power m minus g of x power m, okay, which we know is equal to f of x the whole power m minus g of x the whole power m. But we had just argued that f of x is apparently equal to g of x because that's what we were told. Well, in that case, then f of x power m must also be equal to g of x power m. So that will then become equal to 0. Okay, and all of this is in the field f. So this implies that if q of x is equal to 0, then what is that? The polynomial q of y has at least t roots. Right, all of this x, I mean x, for every choice of x power m where m is coming from this group G will happen to be a root, and this is a contradiction. Because we know for a fact that q is a polynomial whose degree is strictly smaller than t, and apparently now I'm saying that it has more than t or more roots, which is a problem. Okay, so therefore q of x is not equal to 0 in the field f implies that all the less than t products are distinct. Okay, so now the last step, we just want to do some case analysis. If it so happens that t is bigger than a, okay, then it basically means that then we have at least 2 power a such terms or such products, because I can take, I mean, basically any subset of them and multiply them together. And since t is bigger than a, I have at most a set subsets. So I have 2 power a is a lower bound in that case. And if t is less than or equal to a, then we have at least 2 power t minus 1 such products. Okay, this is basically take the first t of them, of these x plus i's, and all products, all subsets, whatever, all non-full subsets. So that you are only allowed to take t minus 1 of them. So take just the first t of them and take all possible non-full subsets. So there are at least 2 power t minus 1. And that's it. And that completes the proof. Okay. So let's just go over this once more. So the lower bound is a little more trickier. So what we are arguing, the first thing we argued was that the degree of h is like 2 or more, because that is going to tell us that these guys are all distinct. Because going modulo h of x is not going to suddenly make two different linear polynomials the same. Okay, so they are all distinct. So this tells us that there are at least a such polynomials. But we want to say not just that, in fact, even if we take small products of them, they are still going to be distinct. And the way we argued that was by saying that if someone told us that, look, G and F and G are two different small products, which are different as polynomials, but somehow when I interpret it over the field, I get 0. Then we are saying, oh, in that case, that polynomial ends up having too many roots. What are the roots? It's basically all x power m, whenever m happens to fall inside this group G. So all of them happen to be roots, and that means that I have at least t roots for this polynomial in this field, even though the polynomial apparently has degree smaller than t, which is a contradiction. So it better be the case that that the q of x that you started off with, that is q when interpreted over the field, is actually non-zero, which means that basically all of these t less than t products are all distinct. And now you basically say that, okay, there are at most, I mean, there are certainly at least min of this many things that you have generated in the process. And that completes both the upper bound and the lower bound. And we know that the upper bound and lower bound together is absurd. So it better be the case that if n was a composite number with at least 2 prime factors, which were both large enough, the algorithm must have correctly outputted composite, and it could not have said that it was prime. Okay, and that's it. That's the full proof of the AKS primality test. It's a beautiful algorithm from 2002. I mean, it's basically showed that primes is in P. Okay, it's a surprisingly short algorithm with a short description for whatever the size of the breakthrough in some sense. Yeah, so I guess this is basically I don't want to say anything more here. There's no point starting something new. But over the next few lectures, what we are going to do is we are going to, okay, now we've shown that primes is in P. You're going to somehow try and say, okay, fine. Okay, if a number is not prime, right now there appears to be some reason to say that it is composite. But can we somehow extract factors from these numbers? And obviously we will not do this in polynomial time. But what we will see is like there are some cool algorithms that do better than brute force, that do surprisingly better than just trying out all prime factors within a certain range and stuff like that. And we'll start proceeding with those sort of factoring heuristics over the next few lectures. So let me stop here and maybe just take questions if there are any. There's some parts which were unclear. So I found that there are plenty of lecture notes for primality, that's this AKS primality test that's present online. In fact, I will suggest, I found that there was some scribe notes that I had written from one of the earlier algebra computation thing that I think when Arvind offered it in IMSC or something, and I couldn't understand what I had. So I will not recommend reading those, but there seems to be plenty of other places where you can read up. Anyway, I'll put up these. You'll have it in the Dropbox folder, and this is complete. The only thing that in today's thing that we didn't prove was the density of primes. I mean, if you really want to get to first principle, that's the one thing that we can prove. But okay, that's one thing you're taking for granted. Okay, so let me just stop here and maybe just ask if there are any questions and so on. Okay, so just to maybe reiterate, I mean, the choice of R was that we needed a good R. So this for loop is not really needed, in the sense that you can first run a for loop over R to find a good R and just run the inner for loop if you want. And then there also seems to be better bound. I mean, we were extremely sloppy in many of our bounds. We just kept adding logs whenever we wanted a larger number or something like that. But if you're a little bit more careful, you can improve those bounds, etc. But yeah, all of that is secondary. Okay, cool. So the next lecture will not be on this Thursday because a lot of us are traveling. So I would like to have a lecture on a Saturday if that's okay. I mean, just to make up for many of the lectures that we have lost. But that's something we can discuss over Academy.
Tomorrow will not be the lecture?
No, tomorrow there won't be a lecture. So in fact, tomorrow, the lecture that was originally scheduled for tomorrow was what happened now.
Okay.
So we won't have a lecture tomorrow, and we won't have a lecture on Thursday either. So we'll figure out a meeting next time.
Saturday is fine. Saturday morning is fine also.
Saturday should be fine with me. I'll just anyway send a comment on Academy, and if anyone has a problem, then we can try and find a different slot for it. Okay then.